My name is Haris, and today I'm going to be talking about my project, Coupled Depth Learning. This project is in collaboration with my advisor, Lorenzo Torresani. So, this project is about depth estimation from a single image. And the problem is, given an image, you want to estimate the dense depth map. This is a very this is a challenging problem because the output space is a fairly high dimensional space. It's the order of the number of pixels in the input image. And if you're trying to do supervised learning for such a problem, there's not enough data in the domain of depth estimation. Also, it's hard to find good features that are very good for estimating depth from the image. So, okay, so we now look at some of the existing approaches that address some of the challenges that are faced in solving this problem. Other approaches, in order to reduce the complexity of the problem, they estimate depths on regions, which could be patches or superpixels as opposed to the entire image. And then they reconstruct the entire image by simply doing the same thing for all of the regions within the image. Okay, this reduces the number of the output dimensionality that you have to produce. Also, this means that you have more training examples. But there is one big problem with this, and that is that regions do not capture enough information for you to predict depth correctly for them. Okay, and in this case, we propose that instead of predicting depth at a region level, you should predict it at an image level. Now that is a hard problem, as I was discussing earlier. So in order to simplify this problem, we explicitly decompose depth into two quantities. One of them is the global depth, which is referred to as G, and the other one is a refinement, which when added together will give you back the original depth. Now, in order to actually make this work, you have to define the global depth in such a way so that it reduces the complexity of the problem. So in our definition of the global depth, we start by saying that the global depth should be very, very small compared to the original depth map. This reduces the number of outputs that you have to predict for every input image. Secondly, it should capture high-level structural details and not focus on very fine details within the depth map. And thirdly, and most importantly, it should be shared across training examples. And if it is shared across training examples, then you can represent it with a dictionary on the global depth. Okay, so now the question is, how do you actually go about estimating this global depth that I've just defined? Well, in order to do that, you're going to start by decomposing your training examples on your dictionary so that each training example is now represented by a sparse set of weights. Okay, now you want to predict these weights for every input example, and that should give you the global depth, and that coupled with the refinement step gives you the final answer. Okay, so how do you predict these sparse set of weights? Well, to do that, we leverage existing trained ConvNets, and we use high-level features which correspond to an overall image structure representation, and we learn a model that will predict the sparse depth, the sparse weights using these features. Okay, so that said, now you have everything in place and you can potentially produce depth. But the problem with this is that if you learn these two quantities, the model for predicting the sparse weights and the actual basis independently, then you're going to get very poor results. And so in this paper, we actually propose how to jointly learn these two quantities such that you can effectively compute a very good global depth, which will give you high overall accuracy in estimating the final depth. Okay, and for that, we introduce this procedure known as coupling. Coupling says you want to find a better set of weights. A better set of weights are weights that will increase the reconstructability, but will be at the same time be very predictable. You can use these weights to update your dictionary and get a better dictionary, and you can use your dictionary to improve your model further, and then you can repeat that. So after doing this, we find that the best model and dictionary that are jointly learned actually produce global estimates like this, which after a refinement stage will end up producing final results like that, as you can see on the right side. Now, here's some more examples of indoor scenes. As you can see, we capture both high-level and low-level image details here. And our approach produces the smallest root mean squared error compared to other approaches, one that do inference on the entire image, and 20, which is the latest deep learning-based approach for estimating depth from a single image. We also show results on the outdoor scene data set, and we show that our root mean squared error is 11% better than any other approach. All right, and okay, so to summarize, we present global depth as a way of producing finite depth estimates. And for more details, please visit poster 3B13, and we will be releasing the source code for this. Thank you.